going to start the lecture on advanced reaction engineering. So, today we will discuss about the straight through transport reactors and catalyst deactivations. So, already we have discussed about the catalyst deactivations. So, what are the various way catalyst is going to deactivate when we consider any reactions. So, particularly the gas oil or crude oils, that is when that is going to crack in a cracking reactors or crackers. So, there is thermal cracking or catalytic cracking is there. So, if catalyst is used for the cracking purpose, so then during that process what is happens? So, coke formation is there, that we know, that is the one of the way catalyst is going to deactivate for that particular reactions and in the reactor. So, many way we can means analyze or we can conduct the reactions. So, we discussed about the moving bed reactors in our previous class, that is basically for catalyst deactivated in a moderate decay is there. So, catalyst moving bed we can use moving bed reactors. Now, today we will discuss when catalyst is going to deactivate very fast, then straight through transport reactors, that is STTR reactors. So, that we will discuss. So, when catalyst is going to slowly decay, that we have discussed, and now moderate decay, that also we have discussed. So, when catalyst going to deactivate slowly, then temperature time trajectories we can use. When moderate decay, then in that case we can choose a moving bed reactors to conduct that particular reactions, that would be much more suitable. So, when catalyst is going to deactivate very fast, means within, suppose we have a reactions, there that reactions we are using, means we have to use catalyst, and catalyst we are charging with the reactants inside of the reactors, but catalyst is going to deactivate very fast due to the coke depositions or maybe some other reasons. So, or catalyst agglomerations is there due to the high temperature reactions. So, then when rapid decay is there of the catalyst, so then we have to take out the catalyst from the systems, as a fresh catalyst we can charge and conduct the reactions. So, in that purpose basically straight through transport reactors we will discuss. So, how it straight through transport reactors is there? So, that is basically here you can see a fresh catalyst, this is a straight through transport reactor, STTR, straight through transport reactor. Here phase catalyst will be charged at the bottoms of that reactors, and here gas oil, that is would be fed at the bottom. So, catalyst and gas oil, this is the reactant and this is the catalyst, fresh catalyst, that would be charged at the bottom, and both would be fed from the bottoms, and that would be passed through this tube from bottom to tops, that would gradually move, and see here we maintain the temperatures, and then the reactions will take place within this tube. So, in this type of reactors, the reactions zone is, or reactions, or you can say the reactor is that part. So, a small vertical tubes, or we have to take for this particular reactions, and then reactions will be take place here, and then catalyst means here see the reactants will move top bottom to the top from these tubes. At the same time catalyst also would be moving with that reactants, here reactions will take place, and that catalyst will be deactivated also here, and then it would come to a separators. Separator. So, this is the separator basically, or disengage you can say. So, here's that products that would be come out from here, and then spent catalyst, that is the solid catalyst, would be come down from here, it would be take out from here. As a result, this catalyst again sent back for the regeneration units, there the deactivated catalyst would be regenerated and again into its own the activity, means at the beginning the catalyst was as a phase catalyst. So, after regenerations again that catalyst would be fed to the reactor. So, by that way, so that is the cyclic process will go on. So, here in this particular zone, that is the straight through transport reactors. So, that will discuss. So, this type of reactor I said the gas oil, let us say cracking reactions, where gas oil in the vapor phase or gaseous phase, that would be cracked in presence of catalyst, and then products, some gaseous product maybe that would forms, and dry gases maybe C1 to C4, that is methane, ethane, propane, butanes that may form lighter gas. At the same time gasolines also will form. So, this particular reactor is used for the productions of gasoline from gas oil. Gas oil is the heavier fraction that would be cracked in presence of catalyst, and that would give the gasolines, that is the C5 to C14 within that range of the hydrocarbons that usually come or generates in the petrochemical industry. So, that is used. So, when these reactions is gas oils, that is the mixtures of C12 to C40 branched normals chains hydrocarbons, that may be naphthenes, aromatics are also there. So, these are the all components we will consider. This is a mixture of component gas oil. So, we will consider a single components. Okay. This is a mixture of components, we will consider as a single species or component, you can say component A. All whole mixtures we are considering as a component A, that would be cracked inside of the reactors in this straight through transport reactors in presence of catalyst. And then coke depositions, this coke in the reactions, another component is the coke, that part would be formed and that would be deposited inside of the catalyst or surface of the catalyst. As a result, it would block the surface sides of the catalyst. Okay. So, then in this type of reactors we have to design or develop a design equations when catalyst is rapidly deactivates, and catalyst means here you can see catalyst is solid particles, and here feed oil, that is in the form of vapor. So, vapors or gas oil or crude oils at a particular temperature, it may liquid converted into the vapor that would move at a particular velocity, means a particular volumetric flow rate is there, that gas oil move from the bottom to the top. At the same time, since the catalyst is the solid particles, that is also moving. So, with that gas oil or vapor oil. So, here catalyst has a particular density, particular has a velocity. So, here catalyst, if we consider this is the reaction zones, if it is a circular tube, it has a particular dimension, means diameter is there, and total length, let us say Z length or total length L, means from bottom to here the total height, let us say this is the total length. So, if we know the total cross sections area, total volumes, then the particle density within that or catalyst density, that we can find out. So, here in this type of reactors, so bulk density of the catalyst particles is smaller significantly than moving bed reactors. In the case of the moving bed reactor that we have studied, that is a packed of the catalyst in the form of bed that is moving slowly. So, their gas component or reactant component is less than a straight through transport reactor. Here gas that is in the form of volumes that occupy more of the spaces, and catalyst that is as a small particles that is moving from the bottom to the top. So, therefore, here in this type of reactors, the density, bulk density of the catalyst is less or smaller than the moving bed reactors. So, here see particles that is moving, I said, with the gas oils that is in the form of vapor. So, the velocity or gas velocity and particle velocity, this is the gas velocity, this is the particle velocity, we are considering both are equal, means at equal rate particle is moving and gas is also moving from the bottom to top. So, here you can see fresh catalyst we are charging in the form of spherical particle moving, and at the same time gas oil is also in the form of vapor, it is moving through this tube. So, here we are considering the particle velocity, gas velocity, both are same, and then UP equals to UG equals to U or US we can say. So, this type of reactors we will consider. Now, we are going to do the material balance within a small length and delta V volume. Let us say from here to here we are considering this length is delta Z, very small height we are considering for this tube. Here Z to delta Z, here this location is delta Z, here this location is Z, the difference is delta Z. Okay. So, that also very small, maybe 1 millimeter, 1 centimeter, very small height we are considering. So, within that volumes also would be delta V equals to volume within that particular point. So, cross sections area that we can find out for this particular tube if it is circular. So, it has a specified diameters that is known, that is fixed. So, cross sections area known, and delta Z, the delta Z that is the height we are considering, that differential volumes within that particular element that we know delta V equals to AC into delta Z. So, this is the differential volume for that particular reactors, within that we are going to do the material balance for the component A, that is the reactants. Okay. So, now this is at point Z molar flow rates are for component A equals to FA Z, and at particular Z plus delta Z locations at this particular point. So, their molar flow rate of component A would be of course lower than that or less than that, since there is a reactions is there. Therefore, molar feed rate at this location and at this location should be different. This is inlet and this is particular outlet for that component A at that particular locations. So, within small delta V volumes we are differential volume we are considering. Now, rate of generations part RA, since here's RA we are considering and this is the volume delta V volume. So, this is rate per unit volumes, here's RA equals to mole per unit volume per unit time. So, if we multiply with this rate with volume, so then this volume part will be, we can eliminate this part, this volume, then mole per unit times would be, this is also mole per unit times, FA equals to mole per unit times. This is the dimension of molar flow rate. So, now with the rate if we multiply this, so this would be the, and accumulations part is 0 when the system is steady state. Okay. At steady state accumulation part is 0. So, now dividing both sides with delta Z and taking limits, and then we will get dFA by dZ equals to RA into AC. Since here d delta Z, that is taking limits and dividing both sides delta Z left hand side and right hand side, and after that we are taking limits. So, then dFA by dZ equals to RA into AC. Now, RA equals to rate of components that A reactant, that is disappearance per unit volume RA, and RA primes, that is per unit mass mole per gram of catalyst per unit times. This is the difference between RA and RA primes that we know. So, now if we multiplied with the density of that catalyst or particles, so density that is the bed density, bulk density of that catalyst particles, I said rho b is the bulk density of the state through transport reactors. If we multiply it with that, so then that would be R equals to rho b into RA primes. So, then we are substituting this RA here, then this part would come and this part was there. So, now equations 1 is dFA by dZ equals to RA primes rho b into AC. So, we can rearrange that or we can express in terms of conversion as we did in the last time also. We note FA equals to FA naught into 1 minus XA, dFA equals to, if we differentiate this, FA naught is the constant. So, therefore, we are taking out outside and dFA equal to minus FA naught dXA. We can substitute this into here, and this for the deactivation rate, how we can express for deactivations or deactivations of the catalyst RA prime at T time, we can write activity into rate at T equals to 0. So, this way, that is the definition of the activity and rate. So, now this RA prime at T we can substitute here. Okay. So, then in equations 1 we can write dXA by substituting dFA, and then rearranging, and then RA primes we are substituting here. Okay. So, RA prime if we substitute, then dXA by dZ equals to rho b AC by FA naught A T minus RA prime T equals to 0, that equation 2 is coming. Okay. So, here I said that catalyst is moving at a particular rate within that particular distance or height of that particular means zones where the reactions was taking place inside of the tube. So, if this also we have considered particle velocity, gas velocity, that is equal to same in this case. So, the contact time that catalyst take part in the reactions, that would be the time the catalyst has been spent inside of the reactors, as we did for the moving bed reactors. Similarly, here also straight through transport reactors. So, let us say Z distance the reactor is travelling at a particular particles is moving at a UP or UZ or u velocity that is moving. So, then the time is required the to reach that height, means from it has a particular moment. So, how long it would take to reach here. So, then the times equals to z by u p if we considered. So, then we can write that a t, that is the activity. So, there we can substitute t in terms of the jets. So, activity we can write in terms of height, means if you look into that here, if it is a fresh catalyst is there. So, here spent catalyst would be spent catalyst. So, spent catalyst is moving here and a fresh catalyst from the bottom of the reactors, reactions will take place, catalyst deactivated and slowly, and then spent catalyst would be here. So, then the activity changes along the height. So, we are expressing earlier one, that was the times, now we are expressing in terms of z, that is the height, means here activity, here activity, here activity would be different along the height, the activity gradually decreased. So, now the mole balance equations we can write in terms of this also. Okay. So, here this activity terms we are expressing in terms of z only. Okay. Rest of the terms remains as it is. Okay. So, now we know that molar flow rates or molar feed rates of component A, that is equals to if we know the volumetric flow rate F A naught equals to V naught into C A naught. This V naught is its units meter cube per time or dmq or mq per unit times, and this is concentrations, it has unit mole per here meter cube, let us say meter cube. So, if we multiply this, it would be mole per unit time. Okay. So, here's u0, it has a here's mole, if you know the volumetric flow rates, velocity and cross sections area, this it has units meter per second and cross sections area meter square, then it would be meter cube per second. Okay. So, volumetric flow rate, it has unit meter cube per unit times. So, this is, so here's F A naught we can write in terms of E 0 into A c and into C A naught. So, now in that equations F A naught was there, that we can replace in terms of this U naught A c and C A naught. So, now these equations would become this after simplifications. So, A c we are eliminating this part, cross section area part, and then in terms of equation 4 is the differential equation of straight through transport reactors, how the conversion changes along the length or height of that particular tubes or the reactors where the reactions was taking place, and that movement when catalyst and that reactant or gas wells, so that is moving at a particular velocity, then along the height or increasing the heights, that catalyst is gradually going to deactivate. So, how it is deactivating? So, that we can easily find out by solving these equations. If we know the parameters component rho v, that is the density, total length, particle velocity, gas velocity, C A naught, these are the component, and of course, the rate of the reaction. So, in the next parts means here you can see this is the differential equation, that the same equation. So, what was here equation 4 we are writing here. So, if we solve these equations by providing all known parameter in the right hand side of the equations 4. So, then this also similarly will come x axis, if we put z instead of weight of the catalyst, since this in the moving bed reactors we have put W here in the x axis, and in this particular straight through transport reactors we are putting z, height is important. So, and x axis conversions, at the same time activity also the conversions is varying this way and activity is moving this way. So, here's one example is given. So, this is the reactions you can see, means whatever we have discussed so far for the straight through transport reactor, step by step calculations you can see. First we have to consider the what would be the reactions stoichiometry is very important. A is going to B plus C plus coke formation is there. Next step is the rate law. Rate law may be this with activity. So, the rate of reactions means for this particular reactions rate law, here we have taken this is not linear rate law, it is non-linear type of rate equations that can be developed for this particular system that was developed based on the experimental result. So, here so many constants are there, k prime, ka, kb and kc, these are the rate equation or rate constant parameters. So, if these are the components should be known for this particular reactions or the systems. So, therefore, once we know this particular rate equations, so then that rate equations we can substitute it here. Then activity rate law also we know, decay rate law, number 3 is the decay rate law. So, decay rate law we know, if we consider the decay rate law is following like this. So, A t equals to 1 by 1 plus A t to the power half. So, this is the some constant is there. So, that constant should know, means the catalyst is going to deactivate. If we study that experiment, if you have to consider or you have to conduct the experiment, and based on that the activity how with times how they are related, this part we know, this rate is known, this part is known, these two we have to substitute in the design equations. Okay. So, before that, so if A t we can time we are expressing in terms of z by u p I said. So, then activity also these equations decay rate law we can express in terms of this also. For one example, if let us say A is that much at 7.6, that is a numerical value that it is known for a particular system, then u p we can write if there is a volume change, cross sections area, concentration of the component A, partial pressure of component A, component B, component C, these are the things are known. Then we should put it here in the rate equations, in the rate equations P V part that is in terms of conversions. So, in the rate equation is known. So, then decay rate law and reactions rate law both are known, and the components means parameters are known or given for this particular system. So, then that we can get it, and then we can substitute in these equations. Okay. So, here see in this case A z by u p in terms of the times. Okay. So, z time we are replacing in terms of z by u p. So, we can substitute this, and this rate equations we can substitute it here, and after that dx by dz whatever the differential form of equation will comes dx by dz. So, that we can solve by using ordinary differential equation solver. So, then the corresponding conversions and z of the reactor length, so we will get. So, this way we can study the straight through transport reactors, how with the length of the reactors the reactions is taking place at the same times the catalyst is going to deactivate. Both we can study, means both the reactions is going to simultaneously occurring inside of the reactor. So, catalyst deactivations is there, at the same time catalyst is means taking part in the reactions is going on, both simultaneously is taking place, both the reactions we can coupled in the design equations we can means put in the design equation, and all the known parameters in the rate equation known parameters, decay rate law known parameters, means component let us say A are known, and z u p these are also known, means total length of the height or that point where the reactions will take place, that we know, particle velocity, gas velocity known, and these are the known. So, then we can solve these equations easily. Similarly, as we did for moving bed reactors or packed bed reactors, the equations we have solved. Similarly, this also for straight through transport reactors also the we can solve. Okay, similarly. So, thank you. So, today is up to this, and next day we will discuss about some other reactors. Okay. So, thank you.